Okay, so today I'm going to be talking about, um, let me just rub these notes quickly. Where did I put these ones? Give me a second, I just lost something. Okay, it's working. Yeah, so I'm going to be talking about pretty much zero form symmetries and understanding them as topological standard defect operators. So last week's one with Jesse, we were pretty much talking about, oh, I need to make sure this is also muted on the iPad. We do this. So it's muted. Yeah, I think that's as far as I can go. Um,
It
but yeah,
sounds fine. It sounds fine.
yeah, last week we were talking about understanding QFT as a category theory, functorially. So as far as I'm aware, there is no explicit construction outside of topological field theory, but it's sort of like the general aim and ambition. For this one, I'm going to shift focus a bit, and we're just going to understand how um, zero form symmetry, so ordinary symmetries, can be understood topologically and as, in particular, extended defect operators. Okay, so let's do this. So lecture two, um, symmetries as defect operators. Cool. Okay, so the general idea that I'll be working with is we're going to start from the classical theory and then we'll work our way up towards quantizing it. So from the classical perspective, for a field theory, usually we start with a Lagrangian, and this allows us to construct an action. So we integrate over a general space-time manifold. And maybe I can disconnect from the audio. Let's try this. Okay, so you basically start with one of these operators, sorry, with the Lagrangian, and this allows you to define an action. So suppose we're integrating over d-dimensional space-time, then you construct the action as follows, like this. And in general, this is going to be then have some field content, which is embedded inside the Lagrangian. And then the standard picture is, say, suppose we have a symmetry. So if the Lagrangian has, say, like field content phi, then you may have a symmetry which acts as phi goes to phi plus alpha, some parameter, some small infinitesimal parameter, um, delta phi. So then the idea is that you want your symmetry, you want your action to be invariant. So classically, um, yeah, it's just going to go to, the action's going to go to S plus delta S. And then from this, we're able to construct our nova charges. In particular, we have two variations, which is allowed. In total, we want the variation of the action to be a total derivative on the Lagrangian. Um, yep, something like this. Let me just check. Oh, and we actually want it to be, yeah, there's some field content here. So we're allowed to be like this. So there's going to be a total change in variation of the Lagrangian like this. And then this allows us, but then if we do it the other way where we vary the field contents and space-time dependence, then we will get the total variation of the Lagrangian as, let me see, what do I write down? Give me a second. Yep, so it's going to be, let me just pull this up. I had this written down somewhere, but let me just find this. Uh, so it's going to be under Novasphere. We can construct the Nova charges or to conserve currents. That are going to be uh, like this. We're going to have Let me write like this. And then if the variation also has space-time dependence, then we also have the change of the space-time coordinates like this. And then the idea is we want to compare the two of them to be independent. So then we're able to construct a total conserved current J0 is going to be 0, where here we have one of our nova currents going to be something like this. Where J is going to be the total change of the Lagrangian, with the derivative as well. Okay, so we have our conserved current, in which case, if we have a Lagrangian, it can be constructed explicitly. But in general, if we just suppose it does exist, then we just need at least a conserved current. For our symmetry is going to be the total partial derivative, the partial derivative like this, and which we can re-express in terms of differential forms as the exterior derivative of the Hodge-Joule of the current, and then this is going to be 0. So here we have J is a one form in the language of differential forms, and then from this, the idea is then we're able to construct charges, in which case they're going to be conserved topologically. So for example, if we take a time slice, then we can construct, let me say this is like the total volume here of our space-time. We might want to take like a time slice, sigma, which will be, say, this top region here. And then we can construct a charge on it. Q is going to be the integral over the space-time slice. I'm just going to do d minus 1 x. And then we have 0 like this. Okay, but we don't actually need to construct it in such a rigid way. We're also able to construct these for any one codimension surface. I tried to do some digging and try to understand, say, why necessarily we want it for time slices. As far as I'm aware, we're able to also do it for any other codimension one surface. But this is something I haven't been able to quite clarify. So this is something I'm still looking into. But the general idea is that then you want to you can construct a general charge. Say instead of on this rigid surface, on the surface here, it could be some other surface like this. I've let it go outside, but that doesn't matter so much. So let's just call this one like sigma dash. Then we can construct a charge. Q is going to be sigma dash. And then in the language of differential forms, let's actually just write it like this first. Then you want the currents to be tangential. Normal. So you want to construct the normal currents to this on projected, where n is going to be the normal vector to our surface. But what we can do is in the language of differential forms, we can just rewrite this as star j. And then so we have these arbitrary charges constructed like this from our conserved currents. Okay. Now, one of the nice things about this is these charges are in particular going to be conserved. So if we say have two surfaces like this, hypersurfaces, codimension 1. Oops, what's happened? I think this has vanished. Let's do this. So if we take one surface down here, sigma dash, and then so we take the top surface up here, sigma. Then the general idea is that these are going to be connected with a boundary. I'm just going to have this in red. And then I'm just going to call this boundary. And let's say the interior volume is just going to be V, like this. So we have the general idea that the boundary of V, oh, let's also pick orientation, like this. And up here. So I'm being a bit, this is a bit informal, but let's just say plus is being sort of like a, was it connected sum of the two surfaces. So you can say that the boundary is then going to be sigma plus this boundary B minus sigma dash. So then the general idea is that if we have, if we integrate over this volume V, and we assume that there are no operators or currents, sorry, source terms inside, then we're going to have that the integral of the exterior derivative of the current is going to be 0, because this is just integration over 0. But if we assume that there are no internal charges or source terms inside this volume, then and also assume it's compactly supported and finite. Oh, and also, yeah, non-divergent. Then we can apply Stokes' theorem. So applying Stokes' theorem allows us to then evaluate this over the boundary. So now we get star J. Okay. Now we can separate this integral into the sum of 3 different ones. So we have the first surface term, which is going to be star J. And then we're going to have the minus the second one. And then we're going to have plus the boundary term. Okay. So therefore we have, I'm also going to orientate the, yeah, let's leave it like this. Yeah, let's orientate the boundary negative so that this is a little nicer. Okay, so then we have that the charge on the top surface is going to be equal to the charge on our other surface plus the charge on the boundary. And if we assume that the charges go to 0 or the currents go to 0 along this boundary, such as, say, if we take our slices to our sigma slices to be infinite, then this is one way to do it. But in general, if we suppose this is 0, then this allows us to say that these charges are conserved. So for example, in just the general setup of like a conserved Nova charge of time, we assume that the currents go to 0 at spatial infinity. In general, they don't have to though, and this kind of brings up like some of the key ideas in, say, like celestial holography and about like the conserved charges along like the boundary. But in general, we don't have to assume this, and we're not going to worry about this. But then this allows us, this statement here says that charge here is like a topologically conserved quantity. So it basically only depends on the homology classes. So this only depends on the homology class of the surface. What do I mean by this? Well, general for homology, you want cycles, but I just mean in the sense of like, suppose this is our sigma, then we can also attach, I don't know, a handle, something like this, the connected sum of the handle and the surface. And then this is also going to be the same charge. Like you can deform it and you'll get the same charges with fine. But yeah. Oh no, if you let me just think about this. Yeah, I actually want to be a bit careful about that statement. Can you add these handles? In general, probably not, but I'll come back to it. I need to think of it a bit more about that before I say that properly. Okay. Anyway, so we have that as our charges. Okay, so they're going to be conserved. And then the general idea is now we want to go into the quantum theory. So now we want to construct the the charge operators. Sorry, the symmetry operators. So in the literature, it's a little bit confusing exactly what they mean by some of these objects, but they construct the charge symmetry defect operators as e to the I lambda times by the charge of these surfaces. So here after quantization, you make Q sigma is going to be the charge operator. Okay. And then what we're doing here with these ones is we're now promoting lambda here to be the algebra valued from like a group action of G, where without the charge, so if we have like a unit charge, this is going to be, let me write it like this. G is equal to e to the I lambda. So here we have G in G, and then lambda is in the Lie algebra constructed from G. Okay, so I've spent a bit of time trying to unpack exactly what it means when we compose these two objects. It's not quite clear to me yet, but I'm still trying to work on understanding what exactly these things, how you compose the two together means. Because in general, we want, when we compose these two symmetry operators together, we want it such that they act like a group. So we have one element on the same surface, and we have a second element on the same surface. And when we compose these two together, we want it such that we get the composition of the two together. Okay. So what we need for this is we want to, if we just evaluate this directly, in general, they do claim that these hold for arbitrary symmetry operators, but we can also try and compute this explicitly with the symmetry operators we construct from the Nova charges from our classical theory, from the quantization of the classical theory. So, okay, so if we try to do that, we get U1 sigma U2G sigma equals e to the I lambda 1 Q sigma e to the I lambda 2 Q sigma. And then in principle, what we need to do is then we need to apply, because these are now Lie algebra valued, we need the Baker-Campbell-Hausdorff formula. So let me just remind of this. This is going to be, if it's e to the x, e to the y, we get e to the z, where z is going to be x plus y plus a half the commutator, and then it's going to be plus other terms where it's going to be like a commutator of x, y, this sort of thing and so forth. But let's not include that. Okay, so then you need to apply these two together. Okay, so one of the other things, oh, I didn't mention this previously, but when we try to do this formula, we need to, if we try it, one of the things that is sort of implicit with this, that isn't explicitly stated, especially like in a lot of the literature, is that these sort of things evaluated only well-defined, say, within correlation functions. So a lot of these things may be written without explicitly using the correlation functions. I think this calculation only will work, this one here, if we put everything inside a correlation function. They may hold outside, but I haven't formally done the proper calculation yet. But let me just sketch what the key details of what we need to do are. So the first thing we need to do is we need to use the operator product expansion of the charges of the currents. Let me just pull this over. Okay, so in general, we will need something. Okay, so if we basically take, yeah, so let me just write down the formula for this one. So I'm just taking from some lecture notes by T.D. Brennan and who's the other author? Let me just confirm this. Seung-Woo Hong. And so I'm just going to quote this one without derivation. So, and then I'll just go through the steps working backwards what we need to derive this. So we need to use one of these formulas for the operator product expansion of two current terms. And then this will allow us to use the BCH formula in order to compute these things. But this one will descend from the general operator, from the Ward identity of the current acting on the symmetry. So once we quantize our theory, the symmetry operators, instead of, say, having the conserved currents like this be zero, we then need it to be in our correlation functions. So in general, if we have an operator defined on the field content, suppose it is under the action of G of our symmetry G, then we're going to have that an operator in representation R of the symmetry will go to the representation of that acting on this. Okay, that's fairly straightforward. And then if we apply the operator product, if we go through the derivation of the Ward identity on this, then we get something of the form, exterior derivative of J X on the operator is going to be, just say, like, if we just do one operator without the usual iterations of our operators, we get something like, yeah, I'm just going to write it like this, and I'll explain in a second. So here, RTA is going to be the representation of the generator associated with the current we produce from the symmetry group action. Okay, but in general, say, what I've seen in the literature is they tend to quote it as without reference to the correlation functions, but implicitly they mean you have to correlate. You have to put the correlator over everything. So that's something that can seem a bit confusing if you just follow it like naively. Okay, but when I write it like this, it means implicitly I'm doing correlations over putting inside a correlator function. Okay, then if we replace it with our operator with the other current operator, then we should recover this identity here. Yeah, so I haven't gone through the calculation details of deriving this one, but in principle, it should hold out. But yeah, okay. So now that we've done that, and we have that they're group light, the next thing to check is that one, the UG operators, the symmetry defect operators, these are going to be topological. So we claim that these are going to be the same as another surface, where this is just going to be in this like a deformation of the original surface. Okay, so if we start just with this, then we have e to the I lambda, the integral over the surface of the current. Or let's just write it back in terms of the charge. Okay, but as we said before, our charges are going to be topological. So then we can just deform it like this. And then that will give us the same thing as before. Okay, so what that gives is that if we say have something like this, we could then deform it into some other surface. Green, I'm just going to do this. And then the two things should be the same. So the green one is going to be this one, sigma, oops, sigma dash. And then this blue one will be this, just sigma. And then the two should be the same. Importantly with this deformation though is we need to not cross any operators. Otherwise we can't apply, unless we can't apply the Stokes theorem. Stokes theorem won't hold in this case. Okay. Okay. What else? Okay, so we want it. So now we have that before we claimed that these operators act like a group. So they're going to be well-defined group operation. The next thing to show is that indeed the inverses well-defined. So let me put the surface on here. Okay, inverse, sigma. Okay, it's a fairly straightforward calculation of e to the I lambda q sigma e to the minus I. Yep, because this is a G inverse. So then this is going to be G inverse, which is, as it's got a Lie group, I lambda inverse, which then is going to be like that. Okay. Oh, I also forgot to mention that these are also supposed to be unitary operators as well, because these are descending from the quantum theory, and these are symmetries of the quantum theory. So these are unitary operators. Okay. Act like this. And if we apply the Baker-Campbell-Hausdorff formula, the third term of the commutator will vanish. So then we just have I lambda minus lambda, which is just e to the 0, but then it's just 1. So therefore we have that indeed, if we have the inverse, this is going to be the inverse of the operators. Okay. What else? Okay, so the next thing that we're interested in doing with this is to understand how the symmetry operators act on, sorry, the symmetry defect operators act on the point like operators. So just for sense of notation, we have that the currents J1, these are going to be one form currents. And then from that, we construct the zero form charges. And then we have our symmetry defect operators, these ones. And the idea is that these now want to act on the local operators. Okay, so a claim for a useful formula here is that UG of the surface acting on an operator will be given by the representation of this G in which the operator acts with another surface on the other side. Oh, sorry. Like this. So the general picture we have for this one is, say we have a surface like this, and we have a point, that operator OR is sigma, and then the idea is we can evaluate or move the operator, sorry, the surface through the operator, and then we have operator on this side, pick up representation of this. And over here we have our surface like this. Okay, now in this statement though, this is again implicitly needs to be defined inside the correlators. Otherwise the calculations can't be performed. So let me just go through that quickly. Okay. Yep, so the idea is what we actually want to calculate instead is this one. Take the inverse, like this one, and then we want to show it's going to be RG O RX. Okay, so if we evaluate this using our definitions, we have e to the I lambda Q sigma like this. Okay. I don't completely understand, but from what I've seen of reproductions of the calculation online, they seem to commute the operator, the local operator with the charge defect operator on the right. I assume this requires the use of correlators, or in the say the half integral should allow us to commute them. So we write it like this. Oh, sorry, I also need this to be on a different surface. Like this one. Okay. And then we combine the two of them together. Again, we need the Baker-Campbell-Hausdorff formula, but then the commutated terms should vanish. Let me just make it clear, you write this. Like you need the correlators for this. Then we can, if we expand these integrals explicitly, let me do this. We have that Q sigma minus Q sigma dash. So as I said before, these should be equal to 0, but the existence of this point operator means that we can't apply Stokes' theorem necessarily in this case. Instead, let me just clarify this properly. Instead, we need to do, can write it like this. Sigma j. Okay, so then we can, when I write it with the minus, I mean like like as the two with the different orientation, you combine the two surfaces together, and then also implicitly need a boundary where then plus the boundary term, but then we want this to be equal to 0 anyway. Sigma this. So this is a boundary we can apply Stokes' theorem. For the existence of the operator inside between these two surfaces, so if I draw this more explicitly over here, so it is sigma, and then these are connected. Yeah, like that, and so forth. The existence of the operator inside makes me a bit skeptical about applying Stokes' theorem, but it seems to be okay at least. It's just the presence of the operator means that from the Ward identities, the current is not the correlation function of the current is not going to be 0. But let's just apply Stokes' theorem anyway. Let me call this interior volume V. So this is the boundary. Then we apply Stokes' theorem to give just a normal volume, and we get delta J, exterior derivative of J. So then we have UG sigma OR X UG inverse sigma dash is then going to be e to the I lambda sigma V, the exterior derivative of that, times by the operator X. Okay, so the next idea is, say we now want to apply the series expansion of the exponential. Sorry, not N, K. Okay, so this is important that these things are evaluated inside the correlation functions, because recall from the Ward identities, we have that this is then going to be equal to the Ward identity I quoted before was in a Euclidean field theory. So say we do a Wick rotation and we do that. So let's say we've Wick rotated into a Euclidean theory, then we can write down the Ward identity delta D. Oh, sorry, this is J's got an X as well. Let me give it Y actually to differentiate it. Okay. So then it's minus Y, RT J O R X. And then also we need the Hodge star to make this a differential form. Okay, so we've done that. Cool. So now we're able to evaluate this, in which case we pick up delta functions of the current acting on the operator, and we get this is equal to and then also take out the algebra indices from let's write like this, lambda equals lambda ATA. So these are the generators and the coefficients. Then we pick up this k factorial k. Then we have sigma v. We pick up the I'm going to have this explicitly written like y, delta dx minus y. And we also have the representation of the generators, and then also the original operators. So if then we put this all together, sorry, not n, k. Oh no, I forgot k. Uh, Yep. And then this just will evaluate to be unitary, unital. Okay. So then we're just left over with k is 0. Yep. And then we can package this back up into the exponential. Cool. And then in particular, because this is the exponential of these Lie algebra, this is just going to be, this is just lambda in the representation. So then this is just going to be the representation of the Lie group acting on the operator. And then, so indeed, we have the following result that UG sigma acting on this operator is going to be the representation of the Lie group acting on the operator times by the symmetry defect operator acting on the other side. Okay. So one interesting consequence for this is, say, as a corollary, we can consider how a sphere or something homotopic to a sphere at least acts on an inserted operator inside. And so we can basically apply like the same sort of idea where then we move, deform the surface through past the operator, and then the local operator, and we pick up the representation. And then we just have the sphere on the other side. And then we can contract this to a point because there's nothing inside. So then it's just going to be 1. So in particular, we have UG of a sphere will be then acting on this operator will be like this. Cool. Okay, so for example, if our symmetry group was U1, then we have, say, for example, this would become descend from, say, like, electromagnetism. Then the idea is this surface acting on these point operators would pick up a phase charge. So we would in particular get one of these charges. So this, let's say it's got charge Q. If it has charge Q, like an ordinary U1 electromagnetic charge or something like that, then this would act as e to the I times by some coefficient lambda times by the charge times by qx. So pick up these charge as we move through this. In some sense, this is quite analogous to, let me make sure I spell this correctly. I'm just going to quickly Google the correct spelling. The Aharonov-Bohm effect. Aharonov. Yeah. So this is quite analogous to the Aharonov-Bohm effect in particular. Where you pick up a phase as you go around the magnetic field, or in this case, the gauge field effect. Okay. So that's another way of seeing that from these topological defect operators that are now localized, not localized in space. Okay, let me just take a few moments just see if there's anything else I want to mention. In general, the idea is then we want to extend these to, oh, okay. So one of the important details about this is these things can then be generalized to non-continuous symmetries. So in a way to say recap, we started with the Lagrangian, or should I say the classical action, and then we have our nova currents, which implies nova charges. And then from this, we have our symmetry defect operators like this. Now, importantly with this, so far we've assumed that these are sort of continuous groups, so Lie groups, and then lambda will be Lie algebra valued. But we can have discrete groups. So this general framework here allows us to generalize to discrete groups where we wouldn't have a nova current and we wouldn't have, where we can still have a conserved charge, where we wouldn't have nova currents or constructed charges. Discrete groups. And also importantly as well, this will allow us, hopefully, to study non-Lagrangian theories. So a non-Lagrangian theory obviously will not have a nova current and no nova charge. So there should in principle exist some quantum field theories that don't have a Lagrangian description. If there's to be, if you take the perspective of quantum field theory being more fundamental than classical mechanics, then there is no a priori reason that you need a Lagrangian, because this is assuming that you can quantize from a classical theory, but in principle, there doesn't need to exist a classical correspondent if quantum field theory is more fundamental. Okay, what did it say? Non-Lagrangian theories allows you to analyze this. Theories. Okay. So then as we continue through these, through this, then the idea is people extend this to higher form symmetry. So far everything here has been zero form because of the charges being zero form, and then the currents are one form. The surface, okay, so we have zero form symmetry. These charges are I'm just going to label it like this. So this is going to be zero. The charges are going to be one, and our surfaces are going to be codimension one. So it's going to be D minus one. Okay. Then we can keep descending further. We can also, in the next lecture, we should analyze one-form symmetries, which are a natural generalization of this. Instead of studying the local operators like point charges, instead consider, say, like Wilson lines, which we charge under a one-form symmetry. Instead, we have currents, which are going to be two forms. Our charges, let me get this correct. Yeah, okay, this is also going to be a codimension 2 manifold. And then our charges are going to be, let me just check this. In general, you will construct the charge from our two-form symmetry using, integral over these codimension 2 surfaces of the Hodge-Jewel of this. So let me just dimension count this. If this is, there's 2, then this is going to be D minus 2. And then you're integrating this So then this should be wait, let me just check. I'm not going to make any statements at the moment, but it's either going to be zero form or one form, but I need to confirm this. We can discuss about that next week. But yes, in general, the picture will generalize. One other important detail, which is worth mentioning, is that with these chart symmetry defect operators, we also have not just were they topological, but they also were group-like, and in general can be non-abelian. For these one-form symmetries and higher, these are always going to have to be abelian, which is nice. So we're going to be able to move them around each other without having to worry about certain aspects. And then we can also have non-group like symmetry defect operators as well, which is in the whole principle spirit of the category theory of the fusion categories and the non-group like structure, which means there's not going to be an inverse necessarily. Okay. Okay, so I'll leave it with that for now, but if there's any further questions, I'm happy to follow up and then we can discuss that.
Okay. Thank you.
I
Did
think
you
I
have
have
any
a
questions, Jessica?
question. Can you
Oh,
hear
sorry
me?
there.
I think I have a question. I think I missed the definition of the defect operator. What is the difference with normal operator?
So, okay, that's a good point. So the normal operators, say like the local operators, if we have our like, say this is like our space-time, the local operators are going to be acting, say, at a point X, but when we say they're defect just means they're going to be extended. So for example, we'd call this a defect operator because they're going to be extended. In particular for these UG operators, these are defined over a surface. And so we call them a defect because they're not localized, they're going to be extended. So that's sort of the terminology behind defect.
Okay, yeah.
I think technically even just your normal operation insertions count as defects, right? Because I think you just say they're like a zero-dimensional defect if it's a point-like insertion.
Yeah, sure.
I guess
Yeah.
anything that shows up in a correlation function as like a contact term, I think you consider as a defect. It's something present in your manifold.
Mhm.
Okay, yeah, thanks. Zero dimensional defect.
Sorry, may I ask something?
Oh yeah, that's fine.
Thank you. So this story pertains to global symmetries, right? Are you gonna discuss
Yes.
actually gauging and local symmetries as well?
Yeah, so we can also move on to that as well. In this picture, we only need we can gauge, I guess we can also gauge these symmetries, that's fine. But then we need to just be careful with, say, if the theories are anomalous. But in this story that I said, it's all about just the global symmetries, yes.
Right, okay.
I'm not completely sure about the subtle details that could arise if you gauge them.
Mhm.
I mean, I think we'll probably talk about gauging stuff next week, right?
Yes.
And so the potential cost for an operator to not being topological is basically whatever happens at the boundary, if I understood correctly.
Well, okay. It's topological in the sense that you can apply Stokes theorem, which allows you to
Right.
deform it. In basically for all these theories, we want it to be zero at the boundary. In principle, yes. Like these ones here, like for us to move it around, say we move it down to here.
Yeah.
Okay. So we can move it like this, then we need to be careful of the boundary terms.
Mhm.
That's right, that would cause it to not be topological. Another thing that's important is the existence of the if there were like source terms or other defects, because when you have the defects, then if you move it through the surface,
Right.
you're going to pick up. Sorry, if you move the defect through, sorry, these UG operators through another defect such as O, like the OX operators, then you're going to pick up sort of phase terms. So it does, you can move them through, but then they're going to affect the system in that sense, or sort of the correlation functions.
Right.
But yes, in terms of these ones being conserved, the charges themselves, this is purely from the classical theory, but then you need to care about the boundaries, which in general we just say will be zero.
Mhm.
But they don't have to be, but in which case you would need to be a bit more careful with it. That's my understanding at least.
Sorry, also about a few of the like commutations that you used in the proofs. So you said basically everything has to be understood as within correlation functions, and therefore,
Yes, that's right.
right, in the path integral, you can basically move them around and
Yeah, some of them I'm quite a bit hazy on some of them, which I mentioned in terms of say like the commutation of it.
Mhm.
I've been trying to look through some of the literature to try and understand necessarily why they can commute. There may be some sort of some properties which are not explicitly stated, but my assumption, at least at the moment, is that it requires the path integral to commute them.
It feels a lot like the Baker-Campbell-Hausdorff part, right?
Yeah.
For the composition.
Yeah, that's right. That's right.
Thank you very much.
No worries. If there's no other questions, I guess we can end the recording and I'll stop sharing.